Yeah, first question, Suraj. Good morning. Can you please have a session today around 9:30 p.m. as usual instead of afternoon? Sorry, today is not working day. Sorry, Suraj, I can't take it at 9:30. That is only for Monday to Friday. Okay. Any questions? So shall we go to the session? Respond. At least raise a hand. Except Suraj, no one responds. I don't know why. Yeah, yeah. Thank you. Thank you for your response. So we didn't discuss about the switch, right? Credits completed. Switch. Switch will play a vital role. See, today's topic is switch. Switch is used for one to many connections. Okay, it depends upon the application, how many devices we need to connect. And what is the difference between switch and bridge? Okay, switch is used for connecting. I need to write properly. One to many. These are for endpoints. These connections for one port to many ports. For endpoints, okay, it's good to go. Some people may get doubt also. What about the bridge? Okay, now uh, bridge is used for connecting legacy devices. Example, PCI. This is parallel bus or PCI hyphen X. Whenever you'll see X means that is extended version. Most we will use that for servers. in which arbitration is between, yeah, arbitration between ingress and outgress. Ingress is for receiving, egress. Egress is for transmitting. Yeah, between these two, okay. Even in either switch or bridge, towards RC means up towards RC. Root complex means towards root complex means it should be upstream port. Away from RC means this is RC centric, okay, downstream port. So that's it about that. See, TX path will be like this. First, it will do scrambling, encoding, serialization. This serialization, deserialization will be taken care by the uh, SERDES. Encoding, we have a lookup tables. Here I'll write. Scrambling means you know. So that we have map A to 10B in Gen 1 or 2. One 128 to 130 B in Gen 3 to Gen 5. Gen 6 onwards, flit uh, flit and FEC. Serialization, deserialization will be taken care by the SERDES. Frame token encoding. See, here only I'll explain. After that, I'll paste it here. Frame token type. whether it is a ideal or start of SDP means start of DLLP, STP means start of TLP, EDP means end bad. The frame token is four symbols and it is used to confirm that previous TLP is nullified. As nullified, that one nullified or not, this information will be given this. EDS means end of stream. It tells that this framing token is four symbol and indicates as the next block will be OS. Ikkada, here onwards it will ordered sets will be starting. What are those ordered sets means? I'll explain next. Okay, that is TS1, TS2, SKP. Skip, we call it as a skip. See here, these are some special symbols. We'll use K28.5. This name, that some code name. These are all in brackets. The code name. This is called COM symbol. Name is comma. It is used for a lane and link initialization. K27.7 FDH. We will use it this for the start of TLP. Are you getting? And SDP start of DLLP. End means hello. Yeah. Is someone pitching in? Okay, okay. Yeah. Skip is used for different bit rates for communication. Okay. We will send a skip sequence. That is also one of the ordered set only. FTS means fast training sequences used within ordered sets. It should be moved from electrically ideal and electrically ideal isolated. Like that it will switch. Okay, from L0S to L0. Ideal used in electrical electrical ideal ordered sets. Okay, which means if link is ideal, then it will go into low power state. It should be. That's the efficient architecture. A electrical ideal exit. See, whenever a request comes for data transaction, then it should exit the electrical ideal. That will be taken care by the this EIE order set. See, this is our link. This is our link. This is our lane. This is from TX and RX paths. Here I am telling a simple example. See, 4 lanes with 10 bits. Only one pad will be sufficient. See here 2 pads. Only pad is sufficient. See L1, which means this represents the lanes. This all together represent the link. Okay, in this I want to send 10 bits. So D0 to D9. So 10 bits completed. But we are taking 4 lanes, right? So it should be filled. We can't keep it like we can't make it float. It should be fixed. So we will send some pad signals. Those are some special characters we will send, so that all the links, everything will be proper. Packet format proper. It look like 4 lanes 9 bits, but we want to stream it. Whenever we will say stream, at the time comma symbol will be given. See, comma first symbol should be comma. It will initializes the link and lanes. So after that to 9 bits, right? So D0 to D8. Again 2 pads. If pads can be anything. It depends upon the number of bits. Okay. Control character encoding. See, these are some characters. We discussed pad character. That is F7. This is 8-bit. This is a continuous uh, running disparity, negative running disparity, positive. Which one we need to choose? These two are exactly ones complement to each other. See, 0 0 1 1. Now here stream of ones, stream of zeros, 0 1 0 1 0 1. See, exactly opposite. These are for 8-bit. Here we will make it to 4th bit and 10th bit, as we will additionally put it into the into this 8-bit. So look like a 10-bit, but this we are not getting directly. We are not adding. We are adding logically with the help of lookup table. In the lookup table, according to these bits, there were some special codes will be there. In that we will map it. So comma, pad, skip. Okay, STP start of TLP, SDP start of DLLP, end. This will indicate the end. End B. This will ensure that the previous one was nullified. Okay, FTS fast trained sequences. This will this mainly we will use it for the link switching between low power states to active state. L0 to L0S, L0P, L1, L2, L3 like that. Ideal, which means nothing, no data is transferring between root complex to the endpoint. Electrically ideal exit. See, this is, see some example. The some example we are taking BC. This is BC, right? We are splitting that into 3 bits, 5 bits, total 8 bits. This is okay. 10 1 1 here. Here for this equivalent 10 1 1 as per lookup table is this 1 1 1 0 1. Okay, so 1 0 0 as per lookup table is 0 0 1. So we are adding here, here as 0, here as 1. Why? Because it need to maintain the DC balance. For that we are doing. So now it become packet. So we will transfer this like this. Encoding means it is for data communication digital systems like PCI interface. Encoding refers to the process of converting binary raw data into specific format, okay, which is suitable for transmission. The transmission ensures the reliable data transfer like signal integrity, synchronization, error detection. Encoding will add redundancy to make sure more robust against timing errors or electrical imbalance during the transmission. 8 bit encoding, the 8 bit stands for 8 bits of the data, and 10B it's a block. Okay, we don't take individual bits, we'll take you will take in terms of blocks. Okay, 10B for 10 bits of encoded output. This is encoder's input, this is my encoder's output. Along with it adding 25% overhead, 2 bits extra, right? So we'll get to 25% overhead. Symbols and disparity, every 10 bit symbol is to maintain DC balance. What is meant by DC balance? Which means approximate total number of ones and total number of zeros should be approximately same. It need not to be exact same, but it should be approximately same. That's what it is. In these, ones and zeros will be tracked in disparity, which tells the difference between the number of ones and number of zeros in a symbol. Positive disparity means more number of ones. Negative disparity means more number of zeros. So running disparity two types: negative disparity and positive disparity. Okay, which one we need to choose? That is defined by the spec, not us. Why do we perform encoding? The main thing is for DC balancing, and the next thing is for clock recovery, error detection, synchronization and framing. Process of encoding 8 bits, 3B, 5B. See, it will become 4B, 6B. So total 10. 10 bits. It is a one symbol. Input data is this something. Here we are splitting this, each bit we are telling like A B C D E. Okay, this 5 bits, this 3 bits FGH. So we are adding I and J. Okay, then it will become we don't add simply like that, we will take from the help of lookup table. So then it will become like this. So total number of ones 2 in this, total number of zeros 3. So negative disparity, this one. This I have discussed disparity, everything. So you people got some idea, right? So where we have started. Little bit basic is completed. Any doubts? Yeah, I'm stopping the screen. Any doubts? Now I open the actual spec. Hi, please ask doubts. Okay, in PCIe. Now we wrap up all three layers. Now we need to go for actual spec. Suraj, pad means padding where we add extra bits or bytes for proper synchronization. Suraj, are you asking or telling? I'm not getting. Suraj, I didn't get your question. Please type it in the chat. Yes, 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 yes. Yeah, yeah, you are right. That thing only. Any more doubts? Yeah, yeah. Uh, which is special symbol? Okay, okay. Hmm. Yeah, yeah, yeah. You're right. Uh, where we use means I'm not understanding your question itself. Yeah, 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 yeah. See, that will present at the initiator. Who is our initiator? Those symbols will be given by the initiator. Who is our initiator? Who? What is the person name? Sorry, what is our initiator name? Huh? Hello. Who is our who is our initiator, ma? Who will initiate? See, you and me were discussing. First, you initiated, right? Like that in our PCE, who is the initiator? What data link? You are telling protocol stack, and see that a physical chip in a die or a chip, who will initiate that transactions? RC, right? Root complex. You got the point? Mm. And Shiva, an initiator for encoding correct. I didn't get your question, Shiva. What is that? Symbols are used. Yeah, we are using symbols. Any more doubts? So that now we need to go for step two. It is very important. That's why. Shiva, for earlier question that was being asked. Yeah, okay, Shiva. No, no worries. Next, any doubts? Can we go for dog two? Only Suraj Saja. These people are active. Remaining people not even response. I don't know why. Okay, your wish. It's how much you wanna learn. It depends on how you interact. It's your wish. Okay. Now we will go through. Now we will go through little bit level up. So that to we need to go to actual spec. For that we need to go this. Okay. See, where can we find PCI Express? First of prior to PCI, there are legacy standards. That is nothing but legacy means older one. Comparatively, present PCI before some technologies were there, right, to do this job. Those means legacy. We call the terminology. PCI peripheral component interconnect. Express is a popular standard for high-speed computer expansion overseen by the PCI SIG. These people, the special interest group, these people designed that. PCI interconnects can present in all levels of data acquisition system DAC chain, readout boards, storage media, network interfaces, computer accelerators, GPUs, FPGAs, and may even, sorry, and may even more so in the future with the CXL Compute Express Group. Okay, it will act like an interface. It is not an interface. It act like mimic like an interface. It will take PCI output and it will give it to the external memory devices, especially cache. These things. Understanding your data acquisition system requires some level of understanding of PCI Express. After that, we will see this. See, PCI history and evolution, PCI concepts, PCI layers, PCI practical aspects, PCI performance, PCI future roadmap. We know PCI concepts. We went through PCI layers also. Uh, Transaction layer, data link layer, physical layer. PCI practical aspects. Okay, that we will see here. PCI performance. It's too good. PCI future roadmap. We'll see that slowly, step by step. Conventional PCI legacy system. It looked like that. It came in 1992, 32-bit, 64-bit. This is the 64-bit, 32-bit RCI broadcast. 3.3 volts PCI card. It will look like this. Expansion card. 5 volts PCI card. 3.3 volts and 5 volts PCI card. 3.3 volts PCI slot. See, this is a parallel interface and bandwidth 133 Mbps, 1 Gbps. This is entire link. This is per lane. Okay, 32-bit, 33 megahertz. 533 Mbps, 4.2 Gbps, 64-bit, 66 megahertz. PCI example, Atlas filler. See, I'm going little bit faster. If you people can't follow up, please ping me so that I'll go very slow pace. Why I'm going a little bit fast means we already covered all these things. It's like redundancy. So to avoid that, I'm going. If you people want slow phase, you can ask. Is it okay or should I go slow phase? Okay, fine. See, these are all not that much important. This is actually Atlas Filar. Okay, this is PCIe Atlas Filar PCIe. See here, this is the ports. These are the chips modules. Four optical channels. Each channel consisting of 160 Mbps. Total link is 1.28 Gbps. S-Link protocol, 2 Altera FPGAs, bus DMA or PCIe, third Altera FPGAs, 64-bit, 66 MHz PCIe. PCI compatible hardware and software, off duplex bidirectional. Higher bus efficiency, split responses, message signal interrupts. Bandwidth is less than 1.06 Gbps per lane, 8.5 Gbps per the link. These are the things you people CMOS ferrol. This is CMOS people. Okay. Now we came to PCIe. In PCIe software topology. This is the topology. It look like this. These are the expansion ports. Okay. It is serial interface, full duplex bidirectional, bandwidth Gen 4, 16 Gbps with X1, X16, 256 Gbps in each direction. And that too, this is full duplex bidirectional. Okay. Still evolving. Okay. See, Alice Roxy. This is it. Okay. 36 channel up to 6.6 Gbps S channel. 2x DDR SO DIMM. Xilinx what is FPGA. PC Gen 2 X8 channel. Okay. So these are some examples you people can go through. Some people PCIe will look like this. Point to point. This is point to point connection. Serial bus. Scalable link. X1 to X32. Okay. Packet encapsulation. Packet we will encapsulate, which means we will keep within something. What is that wrapper? That I'll explain later. PCI Express device A, device B. Packet we are sending and we are receiving at the same time. That is called bidirectional full duplex. See here, we have Intel Xenon processor based system with NTB. Root, this is some system memory. This bus 0, bus 1, bus 2. This is this root ports. This is PCIe link. PCIe end devices. These are okay. These are some buses. Topology will look like this. CPU, root complex. Here we have memory. PCI bridge to PCI, PCIX. PCI parallel, PCIX for server. Endpoint directly we are connecting. This is called type 0 connection. Through switch we are connecting. So this we call type 1 connection. See, this is upstream. This is downstream. BDF, bus device function. What it will tell is, see, it will tell bus as well as device as well as function. Forms hierarchy based address. Multiple logical functions allowed on a physical device. Troubleshooting with LSPCI. These are all no need to go through. Okay. What are all we need to troubleshoot? Device works is slow. Then what are the checks we need to do? First, link speed, link width, max payload size, interrupts, error flags. Look for bottlenecks upstreams. Device is there but driver fails to load. Okay, unreachable configuration space, unallocated bars, base address registers. PCI concept, address spaces. You know this, right? We have seen it. We will see in next level in detail. This is 0 to 15. Okay, one. This is we call one field. This is 16 to 31. Field 2. We have in configuration space two fields in a address. In the first lower word we have, these are all DWs, right? DW means 32 bit. Double word means 16 bit. So each word consisting of vendor ID and device ID. After that, status, command, class code, revision ID, these things will be present. We will discuss it later. Configuration space bars, either 32 bit bars or 64 bit bars. Capabilities, linked list on Linux. Memory and see, we can either connect to the memory or IO. Most of the applications are for memory. Some even some minor cases even for IOs. See, memory space maps cleanly to CPU semantics. 32 bit address space initially, 64 bit introduced via dual address cycles, DAC. Okay, extra period of address time on PCI PCX. 4 devotes header in PCI, either 4 devotes or 32 devotes, right? I told you, but here we are talking about only 64 bit, so it should be a 4DW only, not 3DW. Burstable, multiple devotes. IO space map cleanly to this CPU semantics. 32 bit address space non-burstable. IO non-burstable, memory burstable. What is meant by burst? Which means burst means it is simple. Even you people will learn it AXA as well. Burst means we will give address only one time. After that, we will send continuous data. That controller logic of that any device responsibility is to uh, uh, decode the next address. That is not burden of your initiator. That is root complex. Bus addresses, physical address, the address of the CPU sends to the memory controller. Virtual address, an indirect address created by the operating system, translated by the CPU to physical. Bus address, and a bus address understood by the device connected to specific bus. Uh, okay. Bridges, single root, SRIOV. Joins two independent topologies. Single address space, non-transparent, transparent. Multiple downstreams, switch we need to use. One root on each side. Each side has its own address space. Downstreams appears in the same topology. Here, needs translation table, addresses are passed, fault tolerance. See, PCI interrupts. PCI read config byte. This is, it will tell the device configuration, and PCI interrupt pin like this. PCI read config byte. Dev PCI interrupt line. This is pin. This is line, and so on. PCI enable MSI. Okay. MSI is nothing but earlier these are hardware interrupts. Because of that hardware interrupt, the problem is either we need to poll continuously, or like that it will fetches the huge amount of CPU's time and time, the clock cycles. To avoid that, these people people made it like a pocket with the help of MSA, message signal interrupts. Device A, that will look like request IRQ. Device to device will go to interrupt routine, interrupt service routine. So uh, IRQ of shared device name cookie, like this it will be present. See, in text, X is subset of ABCD. Like here, this is depends on ABC. This is level sensitive. Okay. What is meant by level sensitive? It don't depends on positive edge or negative edge. In between positive and negative edge, logic high will be there, right? 5 volts or 0. It depends on that. Can be mapped to CP interrupt number. PCI, virtual wire emulation. This is in PCI. PCI virtual wire emulation. We will do emulate it ourselves. Okay, that will be present with the help of MSI. MSI, MSIX, these are also interrupts only. X means extended version, that is for servers. Based on memory write, MSI uses one address with a variable data value indicating which vector asserted. It should be less than or equal to 32 per device in theory. MSIX use table of independent address and data pairs of each vector, less than or equal to 2048 per device. Use affinity. See, CPU root complex interrupt controller will be present in root complex. This is memory in-text message, intia assertion message. PCIX PCIXP endpoint, legacy endpoint. What is meant by legacy? Legacy means PCIX, old versions of PCIe. Vector interrupt ID. See, these are all very simple things. Need not to go through. We went all these things. Approximately doubling the its speed for each and every generation. Yeah, in Gen 4 onwards, we will get one new concept, that is nothing but lane merging. In lane merging, we will sample the bit at the exact mid of the uh, clock. Okay, because it will run with 60 GTS with that high speed. That time period will be very less. Sampling will be very difficult. If we sample uh, uh, about the after or below the thresholds, then we may get a wrong data. That is called we may get instead of 1 we may get 0, or instead of 0 won't be 1, but 1 can be possible of 0, because we are getting far away from the threshold values of my my clock on period. Reference clock maintain at 100 megahertz. Backward compatibility protocol negotiation. These are all. PC Gen 5 double of 1632. Channel channel length less than or equal to 10 inches or 14 inches. More than that, if it is there, then it will become lossy. Up to 2 retimers for longer channels. If it is channel is more, then we need to add a retimers. More complex pre-amplification equalization stages. Equalization means boosting at the transmitter side, and at the receiver side we will do de-emphasis. This is called pre-emphasis. Boosting means pre-emphasis at the same, de-emphasis we will do it at the receiver side. Supports alternate protocols. Okay, even CXL also we can easily integrate it to it. In Gen 6, 2 into 32, 64 bit, speed double for 32 GTS, 1024 Gbps. In NRZ, earlier we used to use NRZ, but when I come to Gen 6, we are using PAM4 signal. Because of that only, it is speed is becoming double, because here we will PAM4 means we will for 4 symbols we will assign 2 bits for a symbol. See, 2 power to 4, right? So 2 bits per unit interval. So within one clock cycle we are sending 2 bits, which means our speed is doubling, right? Lower see, this is like lane merging only. Level of voltages, 2 bit encoding. See, 10 11 01 0. Can you recognize this? This is nothing but gray pointers. Those are okay. 2 bits per lower I FEC, forward error correction, lightweight and low latency, 2 nanosecond. FEC for initial correction, only initial phase only we will correct it. CRC and link level retry for larger errors. Fixed size and fixed latency, lower latency. Latency is also fixed, but data transfer of also fixed. That we will call it as a FLIT, FLIT encoding, flow control unit. This is Gen 7. This is the advanced version. It is coming soon later. You know this protocol stack. PCI Express application layer, after that PCI Express logic interface. These are all everything. These are interface for the what we can say interface for the RC, this application layer, and the remaining application layer to all above data link layer, those are all drivers. This transaction layer is not OSI layer. We will use this thing for it's like a middleman taking software drivers data and driving it to the data link layer. So data link layer will take care of the data integrity and flow control mechanism. Okay, physical layer we will connect into bit stream and we will transfer, and of course line coding as well. This is the opposite direction exactly. FPGA, this look like this. You people go through transaction layer, memory read, memory write, IO read, IO write, config read, config write, messages, event signal, MSI, MSIX. You know this application layer is coming. Okay, coming into directly to TLP. TLP look like this. Header, this red color is TLP. Header, data payload, ECRC. This blue color is nothing but data link layer, and this last STP end, starting packet, end packet. This is nothing but the physical layer. That's it. This is entire split transaction model. See, posted transaction. What is the difference between posted and non-posted? Any difference? Posted, posted, we don't get any response. Okay. In non-posted, we will get the response. Single TLP, no completion. Completion packet won't come in a posted. Non-posted, split transaction model. Okay. Requester initiates a requester. Who is the requester here? Endpoint. Initiated transaction with what are its arguments? Requester ID plus tag. Requester and completer IDs encode the sender BDF. Okay. Who will encode these IDs? BDF, birth device function. Completer. Completer means RC. Requester means endpoint. Executes transaction internally, and required amount of payload it will transfer from RC device A to the device B. That's all. RC's job is that. Completer creates a completion transaction. CPL with the data. Bus efficiency read is different, lower with respect to write. See DMA transaction, PCA DMA transaction. Here what we are doing is, our intention is, this is root complex. Yeah, root complex. We have two processors, two CPU. Please wait a minute. Sorry, I have some work. So better what we will do is, uh, in the evening session we will discuss. I have some work now. REM. Hello, ma. Except Rushendra, everyone leave the meet, ma. Now I have an interview.